So last time we started talking really about significant figures, and we also talked about significant figures calculations. Reminder, as we talked about, there's really kind of a couple of operations that we do. We multiply or divide. And remember that when we do multiply or divide, it is the significant figures that we're looking at. We're looking at whichever one is the least number of significant figures in your calculation. That is pretty much how many significant figures your answer should have. And that is, as we talked about, a little bit different than when we add and subtract. When we add and subtract, we're really looking at decimal places. And it is also the least number of decimal places. So as we might have talked about last time, really the reason why it's the least number of decimal places is pretty much your calculation really is only as good as your worst sort of measurement. So the one with the least number of significant figures, least number of decimal places would probably be your worst sort of value that you have in your calculation. And that's really going to determine, how good or bad sort of your calculation will be. Remember that if you are doing sort of multiple sort of steps, if you will, or multiple mathematical sort of operations, you do just want to kind of keep track of your significant figures. You don't want to round too much until the end. And usually a lot of times it is that sort of last step that really sort of determines what your answer should be in terms of the significant figures. We also talked about density as well. And density is mass divided by volume. It has units of grams per milliliter typically, or grams per cubic centimeter. Remember, there's a few different ways that we could really get volumes, much like what you did in your experiment the other day. Obviously, you could just simply take a volume reading, which would give you how many milliliters there would be. You can also do some measurements like you did with your little wooden block. Take like your length times your width times your height or your thickness, and that would give you obviously your volume here, by taking those type of measurements. And again, they each would be, say in centimeters, would give you a volume that is cubic centimeters. The other really common sort of way to get a volume of an object, like we talked about last time, is volume by displacement. And when you do some type of volume by displacement, you basically have some type of container that has something like water or some type of liquid. You take a solid object and you basically put it in. The result of that is we will see the liquid level rise and kind of have an initial volume and a final volume. And that allows us to get the volume of the object by basically just subtracting those two, our final minus our initial volume. And that is a very, very common way to get the volume of an object just by simply dropping in some type of liquid like water. Remember, density is mass divided by volume. Volume is mass divided by density, and mass is volume times density. I think we talked about the DMV triangle as a way to, again, remember how to properly sort of rearrange that. Any questions on any of that stuff we talked about last time? Okay, then let's take a look at one last sort of density example with we left off at. A student needs 150 cubic centimeters of salt for an experiment. The density of the salt is 2.16 grams per cubic centimeter. How many 1 pound boxes do you need? 1 pound. Thank you very much. 1 pound is 453.6 grams. That is something you need to know. So that should help you out with this calculation. Let's take a look. So obviously we're dealing with density. So we want to think about our formula, which is density is mass divided by volume. We have 150 cubic centimeters, and that is a volume. We also have the density given to us at 2.16. So we really have the density and the volume. So again, if you're not sure, it would make sense, obviously, to solve for mass here. We could rearrange this equation, and mass would equal volume times the density. Now, another way, and as we'll talk about here today, a lot of the ways that they do want you to show your work is a sort of method what is referred to as dimensional analysis. You can plug and chug into this equation But sort of the idea of dimensional analysis we'll talk about here today, and we can kind of demonstrate a little bit here in this problem, is we really use conversion factors to sort of help us kind of get rid of units that we don't want, keep units that we do want. So when we take something like the density in this case, which is 2.16 grams per cubic centimeter, we really could treat it like a conversion factor, and we could use it in the opposite sort of way as well, where maybe cubic centimeters are on top and the grams would be on the bottom. In the first case, we most likely would be multiplying by it. The second case, we would be doing something like dividing by it. So it's sort of a dimensional analysis way that you would show this type of calculation is you would take your volume, which is 150 cubic centimeters. And the idea behind dimensional analysis is this, is sort of like fraction based. So the units that we have here are up on top, which are cubic centimeters. And when we do this, we pretty much go opposites cancel. So we want to get rid of the cubic centimeters. So we do want to this way here, where we put the 2.16 grams up on top and the cubic centimeters on the bottom. What we're doing here in terms of math is we're really multiplying across the top and we're dividing by the bottom here. So we're going to multiply here, come back and really divide by the bottom. The idea of this, though, is this will actually cancel out the units. The cubic centimeters will cancel, and that will leave us grams, which basically we're just going to take 150 times 2.16. That gives us 324 grams of salt would be needed in this case. The reason the units cancel is the same idea. We're basically dividing centimeters divided by cubic centimeters, or cubic centimeters divided by cubic centimeters equals 1. Same idea if you take 4 divided by 4, it equals 1, or 2 divided by 2, it equals 1. So if you take two numbers that are divided by each other, they basically equal 1 or cancel out. If you take two units that are opposites of each other, dividing, they will also cancel out basically. This way of showing it here is what is referred to as dimensional analysis, where you see the units, you see the units canceling, and that is pretty much how they want you to work out a majority, if not most of the problems in chemistry as you go through. So we will do more of this here today. But keep that in mind. That's basically why we did it. They rather you not necessarily just kind of throw the two numbers into here without the units and just kind of get an answer. They want you to make sure that you do show the units. Speaking of that, though, we do want to look at sig figs here, right? And my answer should have how many significant figures? We're basically multiplying, right? First number has how many? 2, right? Second number has 3, which means this guy should end up with 2, right? Which would take us here, which would get us something like 320 grams of salt would be needed. And we want to make sure we also answer the question, which is how many really 1 pound bags or boxes do we need? We would just need 1 pound box. Try that again. 1 pound box. Obviously 1 pound is 453.6 grams. So 1 box would give us plenty with some left over. Any questions on any of that there? So again, you do need to know obviously density, how to calculate the density, figure out the volume, the mass, all these things. Any questions on density? All right. Then we're going to go back to where we skipped last time. So we're going to go back in the notes and pick up, I think, somewhere around here. It's kind of where we skipped off and went to the end in the notes. Table similar to this earlier, but just to remind everybody in terms of these tables, again, this is probably a table you should know. You will come across a lot of these prefixes for chemistry. And here we do a lot of kilo, deci, centi, milli. As you continue on the 1A, you'll see a lot of mega, micro, and nano coming into play. So this is a really good one. A reminder that when we do see this sort of times 10 part, what that represents really is scientific notation of, say, 1 times 10 to the 6th. And we talked about it earlier. Again, a reminder that it's a very common mistake people make. They do sort of switch these things around. So if we had, again, a centimeter, that means that 1 centimeter is 10 to the minus 2 meters. So that 10 to the minus 2 is how much there is in the base unit to one of the prefix units. Again, the base unit here would be meters in each of these cases. And it's not the opposite way around, which again, very, very common error that people make. It doesn't matter the base unit. You could have 1 centigram. That's still going to be 10 to the minus 2 grams. It works the same. If you had something like mega, 1 megagram is 10 to the 6 grams. So again, a reminder, doesn't hurt to say it a number of times. That is the proper way to kind of use those numbers as conversion factors. And obviously you could use, these are equalities, right? And any type of equality, basically write 2 conversion factors for, and you could use them as conversion factors. On a lot of calculators, you can do it in scientific notation, just hit 1 exponent button and 6, for example. If you have the button that's like the EE button, on a lot of those calculators, you can actually just hit the EE button. You know, so I should put the button in front of it. But that's, again, basically what that represents. Any questions on that there? So just to hit some of these length equalities that we talked about, again, these couple here, we do come across a lot. 1 meter is 100 centimeters. A meter is 1,000 millimeters. Again, these are equalities, which means that they're on different unit scales, but they do represent the same amount of that quantity. So any type of equality, you really could write conversion factors. And a couple of conversion factors, for example, that we could write, say for the 1 meter is 1,000 millimeters. So that's one conversion factor. Or we could write 1,000 millimeters is 1 meter. So conversion factors are obviously used in situations where we do want to change the units. We typically do not use, obviously, both conversion factors in a problem. We just use whichever one does it. So if we had 325 meters and we want to know how many millimeters that was, we could use the conversion factor where meters are up on top. So we would use the conversion factor over here. Again, setting it up here like dimensional analysis, 1,000 millimeters is 1 meter. The meters cancel. We're multiplying here across the top, gives us 325 times 1,000. The 325,000 millimeters. Now, again, you do need to kind of get in a habit of showing your calculations like this. This is the way they want you to show it. And in this case, in terms of significant figures, this would be considered an exact value, which means, as we talked about last time, we talked about exact numbers. Exact numbers are basically things that are counted, are things that are definitions or equalities like this. So what we would look at in terms of significant figures is actually our original number here that has 3 significant figures. So our answer here would have 3 significant figures. We also could write it in scientific notation. We talked about a couple last week as well. 3.25 times 10 to the 1, 2, 3, 4, 5 millimeters would be another way that you could report that. Remember again that any number that's written in scientific notation, all the numbers before the times 10 part are significant. Any questions on that there? In terms of volume, definitely you should commit this to memory. That is used nonstop here. Again, that equality of 1 liter is 1,000 milliliters, which once again, you could write a couple of conversion factors for those guys. And again, a conversion factor really is just a fraction, basically. And again, allowing you to do sort of opposites that cancel each other out. We talked about the relationship earlier as well, our cubic centimeters and our milliliter, which equals each other. All right. Also, in terms of mass, we might have mentioned before, again, these conversions here, we do see a lot. 1 kilogram is 1,000 grams, and 1 gram is 1,000 milligrams. These are found by basically dividing 1 divided by the exponent factor that we saw in the previous table. All right, let's get those. So let's talk a little bit officially about writing conversion factors. Conversion factors come from equalities, and equalities again are really, as we saw there, kind of two things that are in different units, but do represent the same amount of something. So for example, here, if we had 100 pennies, that would equal $1, right? So that's an equality. And again, it does represent the same amount of money. And from this guy, we could write two different conversion factors, 100 pennies up on top over $1, or $1 up on top over 100 pennies. We use really these sort of conversion factors to do dimensional analysis, which is called how we show our work here in chemistry. The idea of dimensional analysis is, let's just say you had a couple conversion factors where you had unit A over unit B, or unit B over unit A. And if you were starting, say, with unit A, once again, we would set it up like this to show the units canceling. Unit A would go on the bottom. Unit B goes up on top. Those guys cancel. And we would end up with the unit that we're looking for here. Now, this is just a sort of one-step conversion, but if you had multiple steps to the conversion, you would just keep doing that conversion, obviously, with that, whatever conversion factors you need to get there. So if we had, obviously, $3.55, and we wanted to know basically how many pennies that would be, we would do $3.55. We would use our conversion factor. So once again, our dollars are up on top. So to cancel it, we would go with our dollars on the bottom opposite. 100 pennies is $1. Dollars will cancel each other out. Once again, we're going to multiply what's up on top. So 3.55 times 100 gets us 355 pennies in this case. Once again, in terms of significant figures, that right there, that conversion factor is considered an exact number. So we do not have to worry about it. What happens, I would say, probably in a good majority of time, is if you look at the original number, that's, I would say, a pretty good bet as to how many significant figures your answer should have. Sort of the idea behind dimensional analysis and solving problems like this is we're pretty much only doing multiplication and dividing here. So we're looking at significant figures. So again, whichever one has the least number of significant figures, you know, that's how much your answer should have. And in not all cases, but in cases, the original number usually is pretty close to the right number of significant figures in a lot of cases. Any questions on that there? All right, so that's basically what we just talked about. So here are some common equalities, and it's a good table to sort of know some of the stuff, or a good portion of the stuff that's on there. If you remember when we were talking about units, there's really two types of units. There was really the English unit, which is also referred to here as a US unit, and is also the metric unit. And there's really three types of equalities that we come across in which we could write conversion factors for. There is the English to English or US to US conversion factor, and those are all considered basically exact numbers. So those are exact numbers. And again, what that means is the beauty of those guys is you don't have to worry about them in calculations. You know, you just sort of ignore their contribution to the significant figures. There's also metric to metric conversions, which are also considered exact, basically, conversions. So if you're using any type of conversion factor that came from a metric to metric conversion, bless you, you do not have to worry about really the significant figures that are in that number. The one really where you do have to sort of worry about it or think about it is when you kind of cross over. So if you're using some type of conversion factor that comes from basically a metric to English or English to metric sort of conversion, you should look at the significant figures when you're using it in a calculation. There are a few examples. So if you look back on that slide where we talked about exact numbers, there's a bunch of sort of equalities on that slide. Those are considered exact qualities. For example, this one here is considered an exact quality, and one you should know, 1 inch is exactly 2.54 centimeters. So you wouldn't have to worry about the numbers there. Here at this school, they actually don't want to use this number. So they'd use the 1 pound is 453.6 grams. And that also is an exact number. So for example, though, if you took something, say, like this one here, and we took this equality, which is 1 quart is 946 milliliters, which does pop up occasionally in chemistry. From that equality, we could really write two types of conversion factors. We could write 946 milliliters is 1 quart, or 1 quart is 946 milliliters. So if we were to use either of those conversion factors in a calculation, we actually should look at the significant figures that there are. So typically when you have a factor that comes from, say, an equality like this, there's usually one number that's basically 1. Like we see here, 1 quart is 946 milliliters. So when we would look at the significant figures here, we would actually be looking at the 946. So it would have 3 significant figures. If we were keeping track of it, we would not look at the 1. So that's typically what you would want to ignore, is the 1 part of the conversion factor. Whatever the other number is would be what you would want to look at. And you would want to look at the significant figures in a calculation where it's sort of a crossover between metric and US. Obviously excluding like the 1 inch is 2.54 centimeters and the pound. And, yeah. Well, we're very slow to change. We don't really change. It's just like our system. It's like our system, and then like everybody else uses the metric. So, you know, that's why in your car, right, underneath, right, your miles per hour, right, there's like kilometers per hour, right, and all that. Because you go to Europe or someplace like that, they ain't using miles in most cases, right? They're using the kilometers and stuff like that. So I don't know. It's just we're stuck with what we use, I guess, and nobody wants to change. Other questions? Okay, so again on this chart here, probably a good little chart to know. Definitely, I would say we would come across, you know, this little box here, you know, this side a lot. We would come across here a good amount. Obviously, most of these guys are those table that we just saw, like the 10 to the 6, the 10 to the 3 prefix table. So those are ones we will see a lot, and you should be familiar with them. There's also some things, right, that hopefully should be sort of common knowledge, I would hope, right? Because there's like how many seconds in a minute? It was common knowledge. How many seconds in a minute? 60, yeah. How many minutes in an hour? How many hours in a day? 24. Nobody said 60. People always on exams, they like to go 60 with that. I think it's because they go 60 seconds, 60 minutes, and they go like 60 hours in a day. So those are some common knowledge stuff that obviously you should hopefully have. 16 ounces of the pound is another hopefully common knowledge type of thing that you should have. I say that because I've had people on exams, right? Like, I can't really answer this because you didn't tell me how many minutes there were an hour. So, you know, we hope some people have some knowledge. All right, so let's talk a little bit about conversion factors. 5,280 feet is a mile. That's one that pops up a lot. And again, we can, from that equality, we could write the two conversion factors. Again, they're really just fractions. We will not use both of them. So, you know, if we drove 32 miles and we wanted to know how many feet that was, we would set it up using dimensional analysis. So miles up on top. To get rid of it, miles would need to go on the bottom. 5,280 feet. The miles would cancel. Once again, we're multiplying here on the top and dividing by the bottom, which in this case, there's not much to divide since it's all one. We end up with 168,960 feet. And in this case, we should probably end up with how many significant? 2 here. Ignore it. So we should end up here, which would get us something like 170000 feet. Or if we want to write in scientific notation, 1.7 times 10 to the feet. Questions on up there? Now, sometimes we are given conversion factors within a problem. So if we do something like 65 miles per hour, what that really means, right, is you're going 65 miles in 1 hour, or in 1 hour you are driving 65 miles. Now, if you were to come across this sort of conversion factor here, or you used it in a problem, you would look at the significant figures here in that number. Again, you would look at the significant figures in the 65. That's because obviously it's not like an exact, everybody drives 65 miles an hour, right? So it's not really an exact conversion. So you look at the significant figures here with this particular conversion factor. A gallon of gas, 91, costs $3.05. That was expensive when this was written, right? Now I would jump at 305. That seems good. But basically what that means, right, for every gallon of gas that you pump, it would cost you $3.05. Or for every $3.05 you spend, you get 1 gallon of gas. Once again, here, if you use this in a problem, you probably would look at the significant figures in these numbers when you are using them in your calculation. Also, a very, very common sort of number that we come across, or numbers that we come across in chemistry, are percentages. So a lot of times we're given numbers and percentages, and a lot of times it's very much easier to do the problems by simply kind of converting the percentages into conversion factors. So as you may be familiar with, right, the easiest way to convert a percentage into a usable number is just to assume that you have 100 of it. And what that means is basically the number stays the same. So if I had 12% body fat by mass, for our trick here, we would go 12 kilograms of fat per 100 kilograms of body mass. Or for here, in our English sort of conversion, 12 pounds of body fat is 100 pounds of body mass. So for example, if you had a solution that was, say, 5% by mass, which is what that means, mass to mass, say sodium chloride. If you wanted to kind of use that in a calculation, a very easy way is just to assume that you have 100 of it. And that would mean that you would have technically 5 grams of sodium chloride per 100 grams of solution. Or in 100 grams of solution, you would have 5 grams of sodium chloride. So very common thing that we do in chemistry is kind of convert percentages into conversion factors. And again, assuming 100 is just an easy way to do it. It keeps all the numbers pretty much the same. You could really assume any number you want, but all the numbers change. So it's just easier to assume 100 of it. Any questions on that? So let's talk a little bit about dimensional analysis. So once again, as I mentioned, as I sort of been doing in some of these examples and how to work out problems, they really do want you to show your work through dimensional analysis. It's really what they mean in most cases when they say show your work, is they want to see the setup like I was doing there with the units, the conversion factors, the units canceling, and obviously the answer with the right number of significant figures. So they expect you to do your work that way. They don't expect you to do your work, and unacceptable for showing work is just laying up some numbers. Yeah, so laying up some numbers and an equal sign and like this is the answer. They need some type of structure and form as to how they want it here in chemistry, and dimensional analysis is really the way that they want you to show your work. So as you go through your chemistry career here, when they say show your work, you know, this is sort of how they want you to do it. Step to solve these type of problems. Sometimes it's helpful to write what's given to you in the problem. Also to maybe write what you are trying to find. Write the appropriate equalities. So you want to think about a path that will get you to where you want to finish in terms of your calculation. Now, you want to write the appropriate conversion factors for those equalities. With that being said, there are sometimes multiple ways that you could get to the answer depending on sort of your path of conversions that you choose. So you could take one path of conversions that would get you there. You could take another path of conversions that will get you to the same answer. So as long as you choose sort of legitimate conversions, not ones you made up, you could maybe find a alternative pathway to get to an answer. It doesn't really matter which pathway you choose as long as you show the work. And again, they're legitimate conversions, not just ones that you made up. Most importantly, for here in most chemistry classes that you take, these last two are really what you do need to show to get credit or full credit. And that is to set up the problem like I've been showing with the conversions and the units canceling out. And then obviously you should solve the problem to the proper number of significant figures, and also make sure that you include your units in there as well. Any questions on any of those steps? Now, if it helps you to do sort of these steps, you should do it, but you don't necessarily have to in most cases. But definitely the last two there, showing the setup and the answer, you need to do to get full credit. All right, so we'll skip this since we kind of did one like it. All right, so let's try this one here. You go to a local AM PM, you get yourself a 32-ounce drink at the Thirst Oasis because you're thirsty, I imagine. How many gallons of Diet Coke did you drink? Here are some equalities, which normally obviously would not be given to you, some conversion factors you could get from them. So work through it, get the answer. Again, set it up using dimensional analysis, showing the units, kind of like I was demonstrating there. And take a moment or two, and then we'll talk about it. You know, you want to sort of think about a pathway to get you to where you want to go. We are starting with fluid ounces, and we basically want to get to gallons. So this pathway will get us there. And again, there could be multiple ways to kind of get there. From each of these equalities, remember, you can write two conversion factors, those two for those guys, and obviously these two for those guys. So in these problems, you do want to just start with what was given to you, which was 32 fluid ounces. Again, although not written as a fraction, it's assumed that the fluid ounces are up on top. So once again, opposite cancel. So using our first set of conversion factors, we would want to use these guys here. And we would take the 32 fluid ounces on the bottom and the 1 quart up on top. If I stopped the calculation right at this point, the fluid ounces would cancel each other out because they're basically dividing each other by one another. The units that we would be left in are quarts at this point. We are not interested in quarts as our final answer. We want to get to gallons. So we want to look at our conversion factors. And once again, by setting it up like this, we could clearly see quarts are. We need to put quarts on the bottom, and that would put our 4 quarts down here, our 1 gallon over here. At this point, the quarts would cancel each other out. Questions on the setup here. What we're going to do mathematically, once again, is every number that's on top We're going to multiply. We're then going to come back and divide by whatever's on the bottom here. So we're going to take basically 32 divided by 32 and divided by 4 gets us 0.25 gallons. Again, pretty much exact number, so don't have to worry about the significant figures in this conversion factor. Pretty much exact number here, don't have to worry about it, which means we come back to our original number, which had 2 significant figures. Our answer here would have 2 significant figures as well. Any questions on that? That is the correct answer. 1/4 is not the correct answer. It makes me think you're too lazy to divide. Yes, maybe not for that answer, but I've had people write things like 333 feet per 525 hours. Perfect. Not perfect. Yes. So always divide it out, get yourself a number, take it to the proper number of significant figures. Don't leave really any answer as a fraction. Any questions on that? All right, let's try another one here. You got antibiotic doses as 500 milligrams is needed. If it comes as 250 milligrams per 5 milliliters, how many milliliters were given? Okay, let's take a look. So we got a couple things given to us. We got 500 milligrams. Okay, it should be a decimal. And we really do have sort of a conversion factor that is given to us in the problem, and it's very common that it is. In this case, there's 250 milligrams in 5 milliliters. We could write it like I did there, or if we needed to, we can use it in the opposite fashion, 5 milliliters over 250 milligrams. So once again, one would be multiplying, one would be dividing. So we would start with what was given, which is 500 milligrams. Once again, setting up dimensional analysis, we want to put milligrams on the bottom. So we're going to use it like so with our 5 milliliters over 250 milligrams. The milligrams will cancel. We're going to take 500 times 5 and then come back and divide it by 250. Going to give us 10 milliliters. Once again, multiplying, then dividing. Yeah. Now, in this case, sig fig wise, because this is really not an exact conversion, we should look at significant figures in that conversion factor. This guy's got 2. This one has 2. And our original number has 3. So we should end up with how many significant figures? 2, which means I really probably should lay me up a decimal point there, right? To give me 2 significant figures. You could also do a little scientific notation if you wanted to. Do something like that. Yeah. Question on that particular one there. All right, so let's try another one. During surgery, you receive 5 pints of plasma. How many milliliters is that? All right, so take a couple minutes to see what you come up with here. So taking a look at this, we have 5 pints. We want to get to milliliters. So we could go from pints to quarts, quarts to milliliters as sort of one pathway that we could choose. Obviously, these are the conversion factors you can get for each of those equalities. So we'll start with our 5 pints. Once again, pints are up on top, so opposite. We would want to use the conversion factor here on the left so that it cancels out. 1 quart is 2 pints. Once again, those guys would cancel. And if I stop the calculation right at this point, I would be obviously in the units of quarts. We do want to get to milliliters. So again, the benefit and why you should write this stuff like this, other than they want you to, is you could hopefully clearly see that quarts are up on top. So you know that you actually need to use this conversion factor here on the right, which will put quarts on the bottom so that they cancel. Quarts will cancel. That leaves just milliliters left over at this point. That gives us 5 times 946 divided by 2. Hits us something with a 2365 milliliters that are left. First off, any questions on the setup here? Now, in terms of significant figures, do I have to worry about this one? I don't. It's an exact number. Should I worry about this one? I should. It's a metric to English conversion. So this one has 3 sig figs based off of the 946. And our original number has 2, which means our answer really should end up right there at 2 significant figures, which in this case would be 2,400 milliliters, or 2.4 times 10 to the 3 milliliters would be correct in this case. Any questions on that? So again, occasionally you do get one of those kind of metric to English conversions. You do want to look at it just like we did there. We obviously would look at the actual number, not the one part, but the 946 part of it. I will say, as I mentioned before, in most cases, even though you may have to look at some of these, and again, not in 100% of the time, but a lot of times it does sort of default back to that original number. You'll be pretty close, if not the correct one, if you just want to blindly do it. But again, it won't be 100% of the time. Any questions on that there? Also, versions in one calculation. So if you're doing multiple steps, as you go on, there are instructors that want you to show it all in sort of one calculation. Personally, for me, I don't really care. You could do it in multiple steps. I'm good with that. Just know, though, as you go on, some do want you to do it all in one. So, for example, if you want to get an answer after the first step here, that's fine. And then take that answer, do the next conversion. That's all good. Again, do not round until the very end so you don't mess up your answer. But if you want to do it in parts, just make sure you do take it to a couple of digits past where you need to be, and then you can clean it up at the end. Any questions on that? So once again, for really full credit on these type of problems, you do need to show this without all the scribbling I have here. And then obviously the answer, to the correct number of digits. If it helps you to do the rest of this, you can, but you don't have to do it. So for credit, that's what you need to show, the setup and the answer. Any questions? All right, let's try another one here. Stranded about 125 miles away from home. You decide, hey, it seems like a nice day. Let's walk. And you decide to walk 55 feet per minute. How many days will it take you to get home? Provided you don't stop or die along the way. That's best there. There's some equalities that might be helpful. All right, let's take a look. So we want to go 125 miles. We want to know basically how many days it's going to do that. That's obviously a length or a distance, and this is a rate, which basically is a distance or length per time. And that's really what we're going to use as a conversion factor to go from basically distance to time. We can use it as a conversion factor that we got from the problem as minutes over 55 feet, or we could use it the other way around. We do have a little bit of an issue because our total distance there's in miles and our sort of conversion factor there's in feet. So we cannot use them the way they are right now. We have to do some type of conversion to start with. You can convert the miles to the feet to the miles, however you want to do it. I'm going to convert the miles to feet. So I'll start with the 125 miles. Once again, I will use my equality here to convert it into feet, which is 5,280 feet is a mile. That way the miles will cancel. Will give me 660,000 feet. Nice little walk, I suppose. At this point, we now have our distance in feet, which works really well with our conversion factor that's in feet per minute. So we're going to use those together. Once again, here's 660,000 feet. Feet are on top, so we actually want to use a conversion factor like so. That gives me minutes. and 55 feet. The feet will cancel. Again, the benefit of doing it this way, besides the fact you need to, is we could clearly see that the minutes are up on top, which means that we need to put minutes on. Minutes is 1 hour. Minutes will cancel. Once again, we can see hours are up on top, so you need to put hours on the bottom. Hours in 1 day. Cancel. Now, if we do this, we're going to multiply everything across the top there. It says 660,000 basically times 1. We're going to come back and hit 55, hit equals, divided by 60, hit equals, and divided by 24 and hit equals. Going to give me an answer of 8.3333, a bunch of 3 days. First off, any questions on the setup here? Sig fig wise, not going to worry about this guy. Not going to worry about this guy. Will worry about this guy. This has 3 significant figures. Although this is not my original number. My original number had 3 as well, which means really the 660,000 should be 3. That means that we should really end up here with 3 significant figures for our answer of 8.33 days. Any questions on that one there? I will say as well, if you do something like this where you're doing multiple stuff, and maybe there are numbers up on top, sometimes people screw up by trying to put it all into their calculator at once. And if you do not do it correctly by using parentheses and stuff like that, you will get the wrong answer. So you could multiply as many numbers as you want across the top. You then should hit equals. You then should divide it by the first number on the bottom, hit equals, divided by the next number on the bottom, hit equals, and divided by the last number on the bottom, hit equals. You will always get the right answer. If you try to punch it all in at once, probably won't get the right answer because you did not put the parentheses in the right spot. If you did do the parentheses, you'll be okay, but most people kind of screw up on that. Question on this here. All right, just a couple other kind of conversions here before we call it. Let's say we did have something like 65 miles per hour we're driving, and we want to know how many feet per minute that is. Why don't you give that a go? Once again, 1 mile is 5,280 feet. And also, if I had 4,325 inches cubed, how many cubic feet would that be? All right, so take a couple moments and do these two. Okay, let's take a look since we're getting kind of to the end here. So on the first one, again, the importance of sort of writing this stuff out in this sort of dimensional analysis way is you could clearly see where each of the units are. So you know whether or not you should multiply or divide. Again, on the, say, last problem that we did, I can't tell you how many people, if I were to give you this problem, they would do this backwards. They would multiply when they should divide and stuff like that because they really don't know where the units are. They're just putting numbers and under numbers and stuff like that. So really, really important to sort of keep it spread out like this so you can see it. We basically have 2 different conversions. We need to take miles to feet, which we could use this conversion on the top, and then on the bottom, we got to go hours to minutes. So we could do the top one first. It really doesn't matter. We'll do opposites. So miles will go on the bottom and 5,280 feet would go up on top. The miles would cancel. At this point, I would be in what units here if I had an answer? Feet per hour. So I'm close there, right? I got my top to what I need, which is feet. Then now I need to change the bottom from hours to minutes. So again, writing it like this, we could clearly see that the hours are on the bottom, which means 1 hour needs to go up on top and 60 minutes need to go on the bottom. The hours will cancel. And now we have feet per minute, which is what we're looking for. We're going to take 65 times 5,280, hit equals, divided by 60, hit equals. And we're going to try that again. 65 times 5,280 divided by 60. And I do end up with we end up with looks like 5720, and the units here would be feet per minute. In terms of significant figures, I really don't have to worry about this. I don't have to worry about this, which means I do need to look at the 65, which has 2. So we're looking at something like 5,700 feet per minute. Number stays with the top unit, and it's 1 of the bottom unit. Question on that one there. Bottom one here, it is 4,325 cubic inches. So we could use our regular inch to feet conversion. This would be 12 inches is 1 foot. Will that take care of it? It will not, because we really got to do it actually 3 times, right? We got to do 12 inches, 1 foot, and 1 more. 1 foot is 12 inches. Inches times inches times inches on the bottom is cubic inches, which cancel out. Leaves us feet times feet times feet, which is cubic feet. And we take 4,325 divided by 12, divided by 12, and divided by 12. Gets us really 2.503 cubic feet. 4 significant figures because this number is 4. The rest of them are exact numbers, so we would want 4 significant figures on our answer. Question on any of those there. Now, can you do this? Whatever the 4,325 cubic inches, 12 inches is 1 foot in cubit. The answer is yes, but in my experience, most people actually don't do it 3 times. They just do it once. So I would highly recommend that you maybe write it out so you don't mess it up, but you could do it that way. First off, any questions on conversions or any of those things? That will wrap up chapter 2. The last couple of slides about specific heat, we are not going to worry about. So you don't have to, not specific heat, specific gravity. You don't have to worry about it. So we'll pick up chapter 3 next time.